Now I'm going to do sort of a mixture of stuff that are contained in chapter 10 and some things that are contained in chapter 9. And I'm going to start with a concept that's in chapter 10 called functions. And what you see that I have illustrated here are two correspondence between sets. One set called cities. I should have said cities, and a set called teams. And if you know basketball a little bit, it's pretty obvious that I've on the first correspondence, I've related cities to the teams that are hosted in that city. So, for example, in Chicago, we find the Bulls. In Toronto, we find the Raptors. And in LA, the LA has two teams, the Clippers and Lakers. And there's a team that's not assigned to a specific city, the Spurs, which is in San Antonio. San Antonio is not part of the cities I've listed on the left column, so there's no arrow going to the Spurs. But what's interesting is that we have two arrows going to Clippers and Lakers. So this is what we call a correspondence between two sets. So it relates elements from the first set to elements in the second set. We usually call the first set the domain, the second set being the range. So in the range, you could actually have stuff that are not related to the elements from the domains. For example, the Spurs are not linked to any of the cities, at least, that I have listed. And then on the right-hand side, you actually see the a related correspondence, but instead I've actually listed in the domain teams and in the range cities. So, for example, Bulls are related to Chicago, Raptors to Toronto, Clippers are related to LA, Lakers are also related to LA, and Miami is not related to any of the teams that I've listed here. But the difference between the correspondence on the right-hand side to the correspondence you see on the left-hand side is that for any element on of the domain for correspondence, for the correspondence illustrated on the right-hand side, so this one, there's always a single arrow leaving from a team to a city. Okay, so in this correspondence, if I give you a team, you can only give me one city. There's not a team that actually plays or that's assigned to two different cities. It's only one city. Where on the left-hand side, a city could be assigned to two different teams. Okay, now the correspondence on the right-hand side is what we call a function. So this relationship, I say relationship sometimes, but I guess the right word is correspondence. This is a function. Okay, and a function is basically correspondence which assigns to every element in the domain. Okay, here any team in the domain, a single element in the range. So a single city. On the left-hand side, this is not a function because LA is not assigned to a single element in the range, it's assigned to two. So this is not a function. It's a correspondence, it's a relationship between two sets, but it's not a function. So the word function is a special type of correspondence. So we'll write this up as our first definition. So function, this is what we're defining here, is a correspondence between a first set, called the domain, and a second set, called the range, such that each member, sometimes I say element, of the domain corresponds to exactly one member of the range. So many things in this world are functions. So for example, the color of your eyes. Okay, your eyes have a single color. So for each and every one of you, I can associate your name to a color. But the courses that you're taking, okay, some of you may be taking more than one course this semester. So if I associate to your name the courses that you're taking, there's not a single course that I can associate to your name. This would not be a function. license plate number, usually on cars, is a function. So hopefully for the government, you don't have two cars that have, no, I was going to say something false. There's a single plate number assigned to every single car, and hopefully for the government, if you take a license plate and you associate it to someone's car, that's also a function. So it's a function in both directions here. There's a single plate assigned to a car. There's also a single car assigned to a plate. So these types of functions are even more special. They're called one-to-one. They're called bijective functions. Sorry, I meant one-to-one function, and they're actually called bijective correspondence. So, in this course, however, we're going to look at functions that assign a number to another number. So those are the ones we're going to look at mostly. So I'm going to give you here an example. I'm going to show you a domain. The domain here is all real numbers. The range is also all real numbers. Now remember, for the range, I don't have to have every single element or member in the domain assigned to elements in the range. So, but I will assign to every number in the domain something. Okay, so here's how it goes. I will give you some example of elements of the domain and what they're associated to. So -2 is going to be associated to the number 2. -1 is going to be sent onto the number 1. I'll have -0.5. That's going to be assigned to the number 0.5. 0 is going to be assigned to 0. 1 is going to be assigned to 1. Square root of 2 is going to be assigned to square root of 2. 3 is going to be assigned to 3. And the question is, if I have any x in the domain, what would be the formula here? So I'm looking for an expression. So x would be assigned to what in general? So you have to give me an expression. So I'm looking for an expression. Okay, I'm going to write something that's false. X plus 1 clearly doesn't work, right? If I take 3 plus 1, it's 3 would be assigned to 4, and that's not the case. It's assigned to 3. So you're looking for an expression here that would generalize the specific examples I've listed here. Okay. So try to think of about the answer here, and pause and come back. So if you're clever, you figure out the rule. The rule is the absolute value of the number. So every time I've taken the absolute value of the number in the domain to associate it to a member of the range. So this is the rule we're looking for. Now that rule, okay, we're going to call it, so in general, when we write x, for the general rule, we're going to call that f of x. Notice that this is not a multiplication, okay? Even though there are brackets here, they're going to play a special role, okay? So this is not a multiplication. So this is the first thing to understand. This is not f, or the variable x times x. Okay, that's not what it is. It's f. So you read that f of x. So it's the output. So f of x stands for the output that you get if x is the input. So we could actually say, for example here, f of root of 2. Okay, so the output of root of 2 is root of 2, right? Root of 2 is associated to root of 2. F of -1, so -1 is associated to 1. Okay, that's because we know the rule, right? Our rule is, if the input is root of 2, the output is the absolute value of root of 2. If the input, which is root of 2. If the input is -1, the output is absolute value of -1, which is 1. So if you take the follow-up to this course, or remedial math for Sec 5, it's all about functions. So here we're just defining what a function is. We're going to go in greater detail in the next course. What I want to show you now is that we can illustrate when we have functions that are defined between the set of real numbers. We can have a graphical view, and we do that on the Cartesian plane. So the Cartesian plane will be used to illustrate functions, if we can. We're going to say we're going to graph functions. So essentially here on the x-axis we're going to put the domain. On the y-axis we're going to put the range. Okay, and here maybe let me list again what are the values of f of x for any given x. So remember, f of x, the rule is absolute value of x. So f of x is the absolute value of x here. So remember, if I have minus 2, the absolute value is 2. If I have a negative 1, the absolute value is 1. 0, it's 0. If I have a root of 2, it's root of 2. If I have 3, it's 3. Okay. So what I will do, those are going to be our, so remember, this is the range here, right? So those are the y values. They're going to be on the y-axis. So for example, let's look at the first line, minus 2, 2. It means that, okay, so minus 2, which is right here, is going to be associated to the number 2. So this point here illustrates that minus 2 is associated to the number 2. So minus 2 is in the domain, 2 is in the range. Minus 2 is on the y-axis, 2 is on the x-axis. I get the point, minus 2, 2. So I'm going to do that for every single point that's part of my graph. Minus 1, 1 is the next one. Minus 1, 1. Okay, I have 0, 0. Root 2, which would be somewhere here. Root 2 is 1.4 something. It would be over here. 3, 3. Okay, obviously I could come up with more points just by evaluating the absolute value of x for any given x. Okay. Now x here, I have selected some values of x on the real line, but it's all real numbers are actually considered. So if I would join all those points, right, there are actually many other points here in between, right, here that I didn't draw. So this would be the graph. So this graph here, so that curve that I'm illustrating, would it be essentially the collection of all the points that are part of the graph of the function. So when we see a line here where we should think of it in terms of a whole bunch of points that are essentially forming that curve. Okay, and we would say here this is the graph of the absolute value function. So it has this V shape. So all functions have a certain graph that has some features. Some are better known than others. So we're going to look at the graphs of some important functions. Now to complete this video, I'm going to give you a little exercise to solve. So here it goes. So you're given a correspondence that's a function. So notice there's only one arrow leaving from members of the domain, and you want to find the rule of a function that we're going to call f. So we're going to try to find what f of x is, and we're going to graph, and I want you to graph the function f. So you want to find the pattern, okay, in the correspondence between members from the domain to members from the range. So in other words, given any value of x among the real numbers, you want to find what we're going to call the output f of x. So you're looking for what f of x is equal to. All right, so try to find the rule and try to graph the function afterwards. So one thing that gives away the rule really is the last line before I added x, which is pi is associated to pi cube. So pi was cubed. So let's see if all the other numbers were cubed. Yes, they were. For instance, root of 2, if you cube it, right, you're going to multiply root of 2 3 times by itself. These two roots will become 2, right? So you're going to get 2 root 2. So 2 root 2 is in fact the same as root of 2 cube. And all the other numbers you can check, they're cubed. So the relationship, or the rule we're looking for, actually the rule, is x cubed. Okay? Now, if we're going to draw this, or graph this function, okay, I don't have to select all the numbers I had before. Maybe in a little table I can select a few of them. You see, so with minus 2, it's going to be minus 8. Minus 1, it's going to be minus 1 if you cube it, right? So you cube everything. 0, you cube it, you get 0. 1, you cube it, you get 1. 2, you cube it, you get 2. You get 8. So let's say 1 0 1 2 1 2 1 2 3 minus 1 minus 2 minus 3. And here I need, maybe this is 10 here, 10 there, okay, minus 10 actually. So this would be what, 5, and 1 2 3 4 5, like that. Okay, so 0 0, 1 1, which would be right there, minus 1 1 would be right, actually, you know what, that's not completely true. 5 1 2 3 4. This is actually 1. So you see, sometimes to graph the function, you don't have to have like the tick marks along the x-axis are not of the same length as the tick mark along the y-axis. Have way more, right, on the y-axis, because look at the range of my function. It goes from, well, I have numbers between minus 8 and 8 if I have values of x between minus 2 and 2. So it's easier just to adapt the scaling of your axes to the numbers you have. So 1 1 would be somewhere here. Minus 1 1. No, I did it again. 1 is over there. So 1 1 1 is here. Minus 1 1 is there. Right, assuming this is kind of 1. 2 8. So 2 8 would be where? Well, tuck somewhere over here. 2 minus 2 8 somewhere over there. Maybe we're missing a few points, but if you'd have like you can check what we have. What minus 1.5 is minus 3.37, so minus 1.5 is here. 3 would be right there, and then we'd have the exact same thing. 1.5 would be 3 point something, something like that. So if you start linking those dots together, you're going to end up with a curve that looks like that. It's kind of like an S shape in some way. So this is the function x cubed. That's what it looks like. And that's it. So in the next videos, we're going to look at two important class of functions: linear functions and quadratic functions, because we've looked at polynomials of degree 1 and 2 a lot in this course. We're going to focus on those two types of functions.